Mapping meshes to another domain is a fundamental task in graphics and geometry processing. A well-known application is texture mapping, where the map is used to transfer color information from the 2D texture image to the 3D surface. Another application is hex meshing, where the map of a tetrahedron mesh into a regular 3D domain helps to generate a hexahedral mesh in the source domain. Most applications require the mapping to be injective or one-to-one, that is, any two different points of the mesh are mapped to two different points in the target domain. A non-injective map is not usable for many applications, such as texture mapping and hex meshing. Some applications also require the map to satisfy some constraints, such as mapping into a target domain with a prescribed boundary. More generally, the boundary is not fixed, but the map needs to satisfy some positional constraints. The quality of the map also matters in many applications, such as texture mapping. A high-quality map preserves the geometry of the original shape, while a low-quality map introduces large shape distortion. In this work, we take as input a source mesh and a group of constraints, which can either be a prescribed boundary or a set of positional constraints. We then try to compute a constraint-satisfying injective map with low distortion. The key benefit of our method over existing works is the improved map distortion. An ideal map preserves both angle and error. Such maps are called isometry, but are not available in most cases. In reality, a map may preserve angle but distort error, or may preserve error but distort angle. Most maps introduce both angle and error distortion. For maps defined on triangle or tetrahedron meshes, we are interested in the distortion of maps between a pair of simplices. Consider the linear transform that maps a source simplex to a target simplex. We can quantify the distortion of the linear map by its singular values, which describe the degree of stretch in orthogonal directions. When all singular values are equal to 1, the map is an isometry, which preserves both angle and error. When all singular values are the same, the map is a similarity transform, which preserves angles. When the product of singular values equal 1, the map preserves errors. To measure general distortion, we use an isometric distortion metric, which is defined as a maximum of the first singular value and the reciprocal of the last singular value, assuming that singular values are sorted in descending order. This distortion metric is minimized when all singular values are equal to 1, that is, when the map is an isometry. There are many methods to compute injective low distortion maps. However, few methods can produce such maps while satisfying constraints. A classical method to obtain an injective map is Tott embedding. However, it requires fixing a convex boundary, and it also doesn't accept arbitrary positional constraints. More recently, there are maintenance-based methods that start from an injective map and deform the map to improve map quality while preserving injectivity. However, these methods require injective maps to initialize, which are not generally available when there are positional constraints. There's another group of methods that compute injective maps satisfying constraints, but require changing mesh structure, such as adding more vertices. In some applications, the change of mesh structure is not allowed. Finally, there are methods that recover an injective map starting from a non-injective initialization without changing the mesh structure. Although these methods successfully produce injective maps satisfying constraints, the map tends to have large error distortion. We realize the distortion using a grid line texture and use colors to indicate the isometric distortion metric we introduced earlier. In this work, we propose new methods that belong to this category, but significantly reduce error distortion. Our methods build on existing energies whose minimization promotes injectivity. We modify the TLC energy designed for fixed boundary mapping and the SEA energy for free boundary mapping under positional constraints. Our energy modification maintains their high success rate in recovering injectivity, but significantly reduces error distortion. We began by reviewing the total lifted content, or TLC energy, designed for mapping a mesh into a domain with a fixed boundary. TLC energy measures the area or volume of all simplices in a higher dimensional lifted space. For example, the lifting of a triangle is defined by concatenating the 2D coordinates of each vertex with the coordinates of an additional triangle, called the auxiliary triangle, into 4-dimensional coordinates. In practice, we often use the corresponding triangle of the source mesh as the auxiliary triangle. The lifting is controlled using a parameter alpha, which determines the size of the auxiliary triangle. The lifting of a tetrahedron can also be similarly defined. The auxiliary triangle and alpha help ensure a set of good properties of the TLC energy. The energy is smoothly defined for injective and non-injective maps, so it can be optimized starting from non-injective initialization. Being smooth, the energy is well suited for gradient-based optimization solvers. We can prove that for sufficiently small alpha, the global minima of the TLC energy are only achieved by injective maps, if such map exist. Although global minima are unlikely to reach, since the TLC energy is not convex, we find that TLC successfully recovers injectivity when tested on a large-scale 2D and 3D benchmarks. However, TLC has a major limitation. It introduces large area distortions. Here we show the mapping of a bunny into a cross-shape domain by minimizing TLC energy. To realize map distortion, we show the grid line texture and the distortion metric. The map preserves angles relatively well, but the area distortion is high, particularly near the bunny head. In this work, we provide an explanation for this behavior and then modify the energy to reduce area distortions. To understand why TLC tends to preserve angle but changes area, it's useful to consider the residual of the lifted area by subtracting the signed area of the triangle. When the mesh boundary is fixed, the difference between the residual and the TLC energy is the sum of signed area, which is a constant. So the residual and the TLC energy share the same energy minimizer. The good thing about the residual is that we know exactly when it's minimized, as we shall show next. We first write the residual in terms of singular values, sigma 1 and sigma 2. The common factor A tilde is the area of the auxiliary triangle, which is a constant. Inside the bracket, the first term corresponds to the lifted area, and the second term the signed area. We show in the paper that the residual is minimized when the singular values are equal to each other and non-negative. Here we plot the residual as a function of the two singular values, using colors to indicate residual values. You can see that the residual is minimized along the diagonal, where the two singular values are the same. This corresponds to similarity transform, which preserves angle but not area. Since TLC and the residual share minimizer, this also explains why TLC energy tends to preserve angle but introduce area distortion. Now we modify this energy so that its minimum is achieved at isometry, which preserves both angle and area. We expand the lifted area term and find an interesting term in the middle. This term is known as the MIPS energy, which is minimized by an angle-preserving map. We replace this MIPS term with another term, which is only minimized by an isometric map. We can show that this new residual is also minimized by an isometry, that is, when both singular values are equal to 1. We plot the modified residual and observe that it's indeed minimized at isometry. We call the modified part the isometric lifted content, since its residual is minimized by isometry. Having defined the isometric lifted content for a triangle, we can generalize it for a tetrahedral using a similar formula. We show in the paper that the corresponding residual is also minimized by isometry. Finally, we define the isometric total lifted content, or ISO-TLC, energy as the sum of isometric lifted content over all simplices in the mesh. Our ISO-TLC energy inherits all the nice properties of the TLC energy. It's smoothly defined for all maps, and easy to optimize using gradient-based solvers. For sufficiently small alpha, the global minima of IsoTLC are injective maps if they exist. It also maintains a high success rate when tested on the benchmark. The main benefit of IsoTLC is that it significantly reduces area distortion. Here we compare the two energies on this bunny to cross example. While TLC produces some tiny triangles and introduces large area distortion, IsoTLC produces a map with significantly smaller area distortion. Our energy modification can also be used for mapping without fixing the boundary, but with positional constraints. This can be done by modifying an existing energy designed for mapping a triangle mesh into the plane under positional constraints. The energy called the smooth excess area, or SEA, is defined as the total lifted content subtracted by a term called arc occupancy. Arc occupancy is a quantity defined for the boundary of the mesh. We first replace the boundary edge, which is a circular arc, whose center angle is theta, which is a constant parameter for every arc. We then define the occupancy of the curved boundary as the area with positive winding numbers. Finally, we define the arc occupancy as the difference between the occupancy and the total area bounded by each edge and its arc. SEA energy has many nice properties. It's an upper bound for the total overlapping and inverted areas, so its minimization tends to remove these non-injectivities. SEA is smoothly defined for injective and non-injective maps, and suitable for gradient-based solvers. For sufficiently small alpha and theta, we can prove that the global minima are locally injective maps with arbitrary small overlappings, if such maps exist. Even though global minima are unlikely to reach, SEA recovers injectivity with high success rate when tested on a large 2D benchmark. We modify the SEA energy by replacing TLC by its isometric variant, IsoTLC. We call the modified energy the isometric smooth excess area, or IsoSEA. We show in the paper that IsoSEA inherits all the aforementioned properties of the SEA energy. Compared to SEA, IsoSEA significantly reduces area distortion. Here we map a mechanical model into the plane with several positional constraints. Both SEA and IsoSEA successfully produce an injective map, but IsoSEA greatly reduces area distortion. Next, we show more experimental results. In our experiments, we use an off-the-shelf quasi-Newton solver for both IsoTLC and IsoSEA energy. Since IsoTLC exhibits higher order smoothness, we also implement a projected Newton solver for it. We follow a two-step approach to compute injective low distortion maps. We first compute an injective map by optimizing an energy until the map becomes injective or a maximum number of the iterations is reached. Then if the obtained map is injective, we further optimize the energy to lower distortion until the energy converges or the maximum iteration number is reached. We first evaluate the IsoTLC energy on the benchmark released with the TLC paper, which consists of more than 10,000 2D examples and more than 900 3D examples of fixed boundary mapping. We use the same alpha parameters throughout the experiments and compare with state-of-art injectivity recovery methods, TLC and FFM. All three methods successfully recover injectivity for all examples in the benchmark, but IsoTLC achieves the lowest distortion. To compare map distortion, we compute the average distortion for each example using the distortion metric we introduced earlier, and then count the number of examples with specific average distortion. This plot shows the distortion statistic for TLC and IsoTLC on the 2D benchmark. Observe that IsoTLC achieves an average distortion lower than 10 for almost all examples. In contrast, TLC introduced an average distortion over 100 for thousands of meshes. The average distortion statistic on the 3D benchmark also shows the improvement in mesh distortion, although less significant than 2D, as TLC already achieves relatively low distortion. Here we compare the distortion of IsoTLC and FFM. On the 2D benchmark, IsoTLC achieves about 100 times lower average distortion than FFM. In 3D, the two methods produce maps with similar distortion. One possible explanation is both methods have achieved the lowest distortion permitted by the fixed boundary constraints. Next, we compare the three methods on a concrete example. In this example, we map a mouse into the 2D domain with a fixed boundary. The initial map contains 17 inverted triangles. All three methods recover an injective map. We compare the map distortion by showing the grid line texture and the distortion metric. Our ISO-TLC achieves much lower distortion than both TLC and FFM. We highlight the hand of the mouse and observe that ISO-TLC best preserves the size of the grid. We evaluate our ISO-ICEA energy on the benchmark released with the ICEA paper, which consists of nearly 1,800 real-world mapping examples. In each example, a source mesh is mapped to the plane with up to 20 positional constraints. We use the same alpha and theta parameters throughout the experiments. ISO-ICEA recovers injective map for 82% of the benchmark examples, which is similar to the success rate of ICEA energy. For both energies, failures typically happen when different parts of the mesh cross over each other. We call this the crossing arm configuration. In this case, minimizing either energy results in a mesh that shrinks the crossing region to a point, making it difficult for each part to retract from the other part. Next, we compare the map distortion on the examples where both methods successfully recover injectivity. This plot shows the number of examples with specific average distortion for the two methods. ISO-ICEA clearly achieves lower distortion than the ICEA method. We next show a concrete example. In this example, the initial map contains 63 inverted triangles and several overlapping regions. Both ICEA and ISO-ICEA recovers an injective map. ISO-ICEA achieves lower distortion as shown by the grid line texture and the smaller distortion metric. Observe that ISO-ICEA better preserves the shape of the grid on the legs of the spider. Finally, we report the running time of our method on the fixed boundary and free boundary benchmarks as a function of the mesh size. The blue dots show the timing for the first stage of our method, which compute an injective map. The orange dots show the total timing after reducing distortion. The running time generally grows with the mesh size. The timings are similar to TLC and ICEA and are comparable to FFM on the fixed boundary benchmark. ISO-ICEA for free boundary mapping takes much longer to minimize than ISO-TLC, as it needs to compute the arc occupancy term, which involves a global intersection computation of circular arcs. Notice that reducing distortion usually takes much longer than finding an injective map, as it only terminates at energy convergence, or the maximum number of iterations. In summary, we proposed new methods to compute injective low distortion maps under fixed boundary or positional constraints. The core contribution is an energy modification that maintains a high success rate in recovering injectivity, but significantly reducing area distortion. The majority of the failure cases are due to slow convergence, especially for free boundary mapping. We can improve convergence rate by using higher-order Newton-type solvers. Extending ISO-ICEA energy to 3D is another exciting future direction. Adapting energy parameters to different stages of optimization may further improve success rate and reduce distortion. We welcome you to try out our code and data shared on our project page.